So on day 3 now, we can start with lecture 2. So let's see. So we're going to take a little bit of a jump into analysis today. Certainly at least the first half of the lecture, and at the rate I'm going, probably the whole lecture. Maybe I'll say first before anything else that, I mean, when you're studying, so I mean, we're going to be doing a lot like studying properties of harmonic functions and properties of solutions of the heat flow now on Riemannian manifolds with lower Ricci curvature bounds or bounded Ricci curvature. And it's sort of worth pointing out that the geometric picture of your manifold, what it looks like geometrically, and how the analysis behaves on this manifold are completely tied together. I mean, hopefully by the end of next week, we'll at least have some idea of how you actually show some of these things. But if you have the right tools, you end up seeing that they're the same questions. So you want to say things like you know, at most points of your manifold, it looks geometrically very clean. Or maybe you have a harmonic function. You want to say that its Hessian lives in a certain LP space. And you're going to end up finding out that these are the same questions, even though it takes quite a bit of work and a lot of tools to actually see that they're the same questions. But you do eventually find out that they're exactly the same. I mean, it's if and only if type issues once you find the right way of saying everything. So that this is sort of a key thing. Another thing that's very interesting, if you want to think about it this way, and this is something that I think other nonlinear PDEs do less than you do in geometry, simply because in geometry it's more canonical. But it seems to me other nonlinear PDEs will eventually do this in one form or another, is that we're taking one nonlinear PDE here, namely the Ricci curvature, and we're associating to it certain linear PDEs. And we're saying that we're going to study the nonlinear PDE by studying the properties of these associated linear PDEs. And this is a very common tool in geometry, but it seems to be not so common outside of geometry, but it seems to be crucial. Certainly in these contexts, it's where everything comes from. Okay, so that being said, maybe the best place for us to start here is just to do the computation that we wrote down yesterday. So let's start with this. So we've got our Bachner formula. So again, being able to repeat this computation and do it right is probably the most important sort of exercise you could do between now and tomorrow. So that is, let's just compute the Laplacian, the gradient of u squared, on a smooth function, on a smooth Riemannian manifold, Mg. So how do you do this? Well, you always do these things the same way. You write in local coordinates and you start to compute. So what is this thing when we rewrite it in terms of some sort of local coordinate expression? The Laplacian is just some double covariant derivative, and we trace over the indices. Sort of standard summation convention means if we have one upper and one lower, it means we're summing over our basis and our coordinates. And we're applying this to whatever function it is, which happens to be this. But this itself, we're writing in a certain way, right? We're writing this as dBu. dBu. So we're taking the gradient of u, and we're tracing over the two indices. We're contracting. Now what happens? We take our dA in, and we hit two terms. These two terms are really the same. Remember, I can lower an indice and raise the corresponding indice, that there's no harm here. So really hitting this term is the same as hitting this term. So really this is dA of 2 times dA dB u dBu. I just kept them both lower for the fun of it, but it doesn't matter. I could have raised that one, lowered that one, whatever. And now we had this guy come in here. What do we get? We get 2. Well, if it hits the first term now, this becomes dA dBu times dBu. And if we hit the second term, we get plus 2 dA dBu dA dBu. Though most of you have figured this out by this point, computing in this business is an art form. You will not prove anything until you spend a week doing all these computations 15 times over and over and over again. It's one of those things. You know, If you're trying to prove a theorem, it's like you're building a house, you're an architect, and you're the builder, and these are the tools. You just got to know how to hammer the nail. And if you can't hammer the nail, knowing how to design the house is pointless. You really don't understand it. So it's just one of those things you got to do. It's unfortunate but true. Okay, so what do we do with these two terms now? Well, for this guy here, what I want to do, so what I really want to do, right, is that I want to turn, this is a Laplacian of the gradient of u, but I want this Laplacian acting on u, which means I need to go switching stuff. Now, this is a function, which means I can switch these two with no harm at all and just make this a BA. That doesn't matter. But now I want to switch again. But if I switch this and this, I can do this, but now it's curvature, right? So I can switch and get 2 dB dA dAu dBu. But now I've got to add a curvature term on, right? So this is plus 2 R, and this is going to be A, B, A, C, dCu, dBu. Note, by the way, that if you read 6 books, you will not get 2 of them to probably agree on what the right convention for this is. That's not fair. Half of them will agree, right? It's a coin flip. Half will say this, and half will switch these last 2 or the first 2, right? So up to a plus or minus, I mean, the order that they actually write this in may change. So this is sort of just fair warning, right? So you have to think a little bit every time you do this computation what your convention is. It doesn't matter, but the main point is this Ricci curvature or is this minus Ricci curvature when I trace? That's the real question. And what I'm saying right now is that, well, this is Ricci curvature, right? So one should check from the definition that that's actually consistent. Oh, and now I've got a third term here too as well, right? But the third term is plus 2. But what is this? I'm tracing, I mean, I've got a Hessian of u and a Hessian of u, and I'm tracing all the indices. So this is exactly the Hessian of u squared. And now we're nearly done. So this first term is 2 times, well, this here is the Laplacian of u, so it's the gradient of the Laplacian of u, inner product with the gradient of u. So if we write this without indices, we get gradient Laplacian of u. Gradient u is this term. This is the Ricci curvature. It's applied to gradient u. So plus 2 Ricci, gradient u. And finally, plus 2 times the Hessian of u squared. Done. So this is exactly what we claimed at the end of last lecture, right? And note that, I mean, if this had been Euclidean space, so these had all been partial derivatives, this is exactly what everything would have looked like, right? Except for this one piece here, right, when you did the switching. So, no problem. Okay, great. So now, most of what I'm going to talk about today in terms of estimates won't actually be for harmonic functions. It's going to be for the heat flow instead. More or less one and the same, estimates for one or estimates of the other. The same ideas go into proving either of them. It's going to be a little bit more convenient in terms of things like sharpness and sort of really applications even to actually use the heat flow here. Basically, what is the heat flow? The heat flow is a way of taking any old function and producing a better function, producing a function that's more regular. So it's going to be important here. I mean, a lot in the way we'll actually use this down the road is that we're going to take some function whose geometry we're interested in. But we can't quite prove what we want to be true about, regularity of this function. But I mean, it looks sort of, it is doing what we want, but it isn't regular. But we force it to be regular just by flowing it by some amount by the heat flow. But now we have to ask the question is, okay, how much more regular is it? So that's what we want to answer today, is try to find regularity for solutions of heat flow. So let me be precise about what this is. So the heat flow here, the heat flow operator here, we're going to be viewing, say, a mapping from, it doesn't really matter. This thing extends to a mapping between all kinds of Hilbert spaces, but it's in the space of L2 functions on the manifold with the volume measure. You can just think smooth functions. I don't care. It'll map functions to functions. And the point is that, so HTU, it's defined, so it's a one-parameter family of functions, right? And if you're in Euclidean space, you would probably just write this. And it's defined by the property that ddt of HTU is equal to the Laplacian of HTU. And H0u is equal to u. So it's simply the solution of the heat flow starting at time 0 at u. And we flow it. That's all. I'll try and keep this for a second. Now, what's wonderful here is that the heat flow as an operator, I mean, we can think of it abstractly like this as some sort of operator, right? But it's a very clean operator, right? Whether we're talking about Euclidean space or a manifold or whatever. And what I mean by clean is that it has a very nice kernel. So that is associated to the heat flow is the heat kernel. So as we let and there's several ways of writing it, and I'm going to give you both. Some, depending on sort of what your direction you're coming from, you'll be more familiar with one or the other, but they're the same. So the heat kernel is, on the one hand, something which, for every point x in your manifold, and every time t, it gives you a measure. Or you might be happier if you're sort of coming from the point of view of basic analysis on Rn, of thinking of it saying that for it's just something that, given a time t and a point x, it gives you a function of y, right? But the relationship between these two is I'm just multiplying it by the Riemannian volume measure. The reason it's natural to think this way is that what's the defining property of this thing? It is that if I want to take some function u, flow it by the heat flow, and evaluate what's the value of that function at time x. Well, I mean, thinking this way, it's a pretty abstract thing. I'm taking something, I'm flowing it, and I'm just trying to evaluate the value of the thing after we've flown it. It's not so clear what that is. But the point is that there is this measure here, independent of u, it doesn't matter what u I pick, such that, in fact, to get the value of the solution at time t, all I have to do is take u and integrate it with respect to this measure. So really, for every time t and every point x, there's a measure associated to it that says that, well, no matter what function I pick, I just integrate with respect to that measure, and I get my solution at time t. So that's the heat kernel. Just for the sake of it, right? So on Rn, right, what we just get is the Gaussian measure. Right? So the heat kernel is nothing but the Gaussian measure. And maybe this can be homework. So if we had used the Bachner formula here, then if we could have said that for a harmonic function, then we can drop that first term, right? To say the Laplacian of the gradient of u squared is equal to 2 times the Hessian of u squared plus 2 times the Ricci of gradient u. You can do the same thing if instead of looking at something which is harmonic, if you want to look at a similar Bachner formula for the heat flow, what you can say is that so ddt, so the heat operator applied to the solution at time t. Well, that's equal to, same thing, 2 times the Ricci of the gradient of HTU, plus 2 times the Hessian of HTU squared. You'll go through the exact same computation. You'll just end up to actually cancel off that term there. You'll want both of these things here because this is supposed to be at the heat flow thing. It's a good exercise. Okay, great. So what? So let's maybe state what's really the main theorem from today. So the idea is that what the next theorem says is that it's not just going to give us estimates for the heat flow on a space with a lower Ricci bound. It is, in fact, going to allow us to say that estimates on the heat flow are the same as having a lower bound on the Ricci curvature. This is fundamental in the last 5 or 10 years especially. So that is, maybe before I discuss it, let's just write it. So theorem. And I'm going to list a whole bunch of conditions here just to try to be complete. But they're proved by Thackeray, Emery, and Ladeau. The last guy being French, so I'm sure I'm destroying the name. But really, each of them are proved by some permutation of pairs of these two. I don't remember who proved what. So our starting point is just to look at some complete manifold. Then the following are equivalent. So our first condition, well, that's just that the Ricci curvature of our space is bounded from below by, I do actually want a minus here, right? Check my signs real quick. Yes, minus k. I'll push this up in just 1 second. The second condition is that, let's take a function u. I mean, smooth function, whatever, I don't care. Flow it by the heat flow. We just take it and we solve the equation for some time t. Let's look at the gradient of that solution. So we're looking at the gradient of the function after we've flown it. And we're evaluating at some time x. Then, in fact, this is bounded from above by e to the kt times the function you get by taking, not flowing and then taking the gradient, but instead by taking the gradient and flowing. And then evaluating at x. So for non-negative Ricci, right, there's no exponential term. And it's basically saying, like, heat flow and the gradients, well, they don't commute, but they commute up to sine, right? Did I miss something? No. So you're thinking of so in the right, when I usually do this, I do it with 1/2 the heat flow for 1/2 the Laplacian. So that there's sometimes a 1/2 convention that's distinct. If you do stochastic analysis, you prefer the heat flow with 1/2 the Laplacian. It's the same thing, but time gets multiplied by 2. I decided just to stay with more standard convention for this. So already there's a real statement here. Let's maybe even discuss it before I list. I'm going to list like 3 other conditions that are all equivalent. So note one thing that this says right away, right? It says that if we're on a space that has a lower Ricci bound, then if we start with a function whose gradient is bounded, then after we flow it, its gradient remains bounded. That this is not true for a general manifold. I mean, you can start with a nice Lipschitz function or whatever and flow it by the heat flow, but now, I mean, the Lipschitz nature just gets destroyed in some sort of uncontrolled way. But now we know it's preserved. In terms of more recent progress, note the power of this thing is that it's now, I mean, the fact that these are now equivalent is telling you that there's a way of understanding Ricci curvature that had nothing to do with writing down curvature. Right? So that when I say Ricci curvature, what does it mean? Well, it means controlling the analysis on the manifold. There's a very distinctive way in which it's the same as controlling the analysis on the manifold now. Third condition looks very similar to this one. I'm just going to stick a squared in there. That 2 implies 3 is really easy. Square both sides and just do some trickery with the fact that this is coming from a measure. Right? So you got to use it. This is a heat kernel. Right? And then you can pull the squared inside. But the fact that 3 implies 2 is less obvious without actually going all the way around, though, and getting back to the Ricci curvature condition. 4. So this is one we'll only discuss very briefly, but this is a very powerful one. It's almost the same thing, but it's basically a statement that I can throw something else in here. It's saying that I can throw in up to some silly-looking factor. It's saying not only is this bounded by this, but in fact this plus the squared of the Laplacian of the thing is bounded by this. So it's saying after we flow by the heat flow, not only is the gradient bounded, but the Laplacian's uniformly bounded as well. Although we'll probably not really truly get to it during these 2 weeks, this is a tremendously powerful thing because in some sense, this here is not seeing the dimension of our manifold at all. Right? No matter what dimension that we're in, this is the same condition. But this here is seeing the dimension. This is a very important point. So the most powerful application, things like Harnack inequalities and estimates on, Gaussian estimates on the heat kernel, they kind of come from this one. I've got 2 others that are fun, but maybe I'll just leave it at this for now. There are tons of ways, by the way, at this day. I mean, it's become almost a business to find ways of sort of conditions that are equivalent to lower rate bounds on the Ricci curvature. I mean, you can think of it this way. Every time you find a new sort of condition, whether it's analysis or something else that's equivalent to a lower Ricci bound, you can prove new theorems because it gives you a new understanding of these spaces. OK, so in terms of proving this, I mean, I'm not going to prove the whole thing, but I am going to prove 1 and 3 are equivalent, give or take. And the others are really, they're the same, in fact. I mean, you'll kind of go through the same proof, but with, and I'll do it just for non-negative curvature, of course, non-negative Ricci. But I mean, they're the same plus more terms. Just be a little bit more careful and keep track of some stuff. Okay. So this is, in fact, a great trick. So let's consider the following. Let's consider so I mean, we've picked some time t, so let's show 1 implies 3 first. So we pick some x in our manifold and some t, positive, say, whatever. The 3 is sort of stupid for t equals 0, so we can assume it's positive. And we're assuming here that the Ricci curvature is non-negative. So let's consider the following one-parameter family of just numbers now. And so let's let phi sub s be the following. So we're going to let it be Let me write it, and then I'll say it in words. So for s between 0 and t, we're going to take u, flow it by time t minus s, look at the gradient of this thing, square it, and then flow that by time s, and evaluate at x. Now, offhand, you might very fairly think, why on earth would someone write this down? But there is something very interesting about this one-parameter family of numbers. Namely, if I evaluate, so I mean, this is supposed to be from s from 0 to t. So if I just look at the difference of this thing at the final and initial points, then what do I get? I get, well, at time t, I get ht of the gradient of u squared x minus, well, then at time 0, I get the gradient of htu squared of x. So what am I really trying to do? I'm trying to show this is less than or equal to 0, this quantity here. By the way, when you're reworking some of this, it would be very good just to even do it on Euclidean space. I mean, the proof isn't really any harder on a manifold than it is on Euclidean space, but if you know, you're still becoming familiar with the various notation. The idea is the same. Okay, but now if I have some if I've got some function on from 0 to t, right? And I'm looking at the difference of the 2 points. How can I rewrite this in a way that's actually useful? I mean, this is the fundamental theorem of calculus. So this really says that at the same time, phi t minus phi naught is equal to the integral from 0 to t of dds of phi s. So it would certainly be sufficient to show that this is less than or equal to 0 for all times. If I can do that, then certainly the integral is less than or equal to 0, and we're done. Right? So the key point here, right? I mean, so what I'm working us up to is that we want to somehow introduce into all of this a Bachner formula, right? Because for Bachner formulas, we have signs coming from each curvature. We get to drop that term with a sign now, right? So this is what we're trying to aim for. And now we're taking the time derivative of something involving heat flow, which means we have some hope of actually seeing this appear. Okay, but we need to compute this. What is this? So this is dds of hs is the gradient of h t minus s u squared. Evaluate at some point x, whatever. So we're going to have 2 terms from this. So we can hit the first term. So we get sort of a, it's the rate of change of this function evaluated at the gradient of h t minus s u squared of x. Or we can hit inside the term to get hs of dds of this thing, which is the gradient of what to erase. Well, let's keep this one. And get rid of that one. Okay, but the first term, what is this by definition? No reason to get overtly confused about what's inside this hs. It's just some function, call it g, whatever. So we're looking at the dds of hs applied to some function g. But it's the heat flow. So by definition, that's simply equal to the Laplacian of hs of the gradients of ht minus s squared. And this term here, what is this? Well, if that wasn't dds, if that was dd minus s, or ddt minus s if you want, right, that's just simply the rate of, I mean, it's the first term of the Botner form, right? So up to a minus sign, because I have a minus s inside the heat flow there, the second term here is just plus h sub s of, let's call it minus h sub s of, well, everything on that right-hand side there with the Laplacian. So there's a Laplacian of the gradient of ht minus s u squared. There's a plus 2 Ricci of gradient ht minus s u gradient of ht minus s u plus 2 times the Hessian of h t minus su squared. But now, if Ricci is non-negative, this guy here is always non-negative, and this guy here is always non-negative. So up to a sign, I can certainly drop these things. No, there's a minus sign here, so I reverse the sign. So it becomes less than or equal to what? So this term here, well, this and this, well, I shouldn't cancel them. They don't cancel. They just get signed out. And the first term here now becomes, so I didn't mention this. I should have mentioned this, but that this is an easy but good point to check. If I flow something by the heat flow and then take its Laplacian, it's the same thing as flowing it by taking its Laplacian and flowing it by the heat flow. So what I'm saying is that for any g, let's say, or let's say any h, so no metric confusion, h sub s Laplacian of h is equal to the Laplacian of h sub s of h. I'm going to take this for granted. We'll call it an exercise to see this. This is simply because, the time derivative commutes with the Laplacian, so it doesn't matter. So that means this Laplacian comes inside, though. That's the important part. So this becomes hs applied to the Laplacian of the gradient of h t minus su squared. This term and this term went away, but what's left here, it's just minus h sub s of, well, the same thing, Laplacian of ht minus s, Laplacian of the gradient of ht minus s u squared. Now, cancel, cancel, 0. So in other words, what we've shown when we bring this all the way back is that this is less than or equal to 0, which implies that this is less than or equal to 0, which completes the proof. So you may not fully agree with me with this statement at the moment, but if you ever spent time sort of going through a lot of these estimates, even on Rn, for sort of standard sort of linear PDEs, this is not hard. It is not really hardcore computation. I mean, you got to get a little familiar with it, but it's not brutal. Some of the previous estimates that sort of came before this on Ricci curvature and whatnot, they were pretty brutal. And you're getting out of this what is really a very powerful estimate just by knowing how to commute some derivatives and compute a Botner formula. It's much more natural and clean way of actually getting estimates. Though, experience sort of maybe leads to this opinion a little bit. Less than or equal to 0. No, there's a minus sign in front, right? So this is non-negative, this is non-negative, but remember I had a minus sign. Sure, but this difference here was this minus this. So I wanted this to be less than or equal to 0, right? Because then I would move this term over. Did I say it the other way around? Okay. Where did I miss a sign? On the last step. So this is bigger than or equal to, yeah, but I got a minus sign here, right? So you're just saying what they're saying, right? That you want the sign to switch?
No, in general, vt minus v0, don't we want it to be greater than equal to 0?
Yes, that's what they're saying. So now we're trying to figure out where my sign came wrong. Okay, I designate 30 seconds of staring at this to figure this out, and otherwise we move on, and it's a great homework assignment to figure out where I missed a sign. This minus sign was there because we were looking at DDS of the gradient of ht minus s, right? So to apply the Bachner formula, I need s to be t minus s. Right? I can just throw the t in there. It's a constant, but I need the minus s there. Okay, whatever. I don't care. There's a sign wrong. A hug for whoever finds it. For any smooth manifold, this will be fine, right? I'm using sort of just what you know for a smooth manifold, basically nothing else. If it's not, I mean, I am implicitly using completeness. If it's not complete, it's okay, but you need to be careful about how you define the heat flow in that case. That there's sort of a uniquely defined heat flow even for non-complete things. You just got to be careful which one you're using. So like there's a boundary condition type thing going on, right? So for reasonable boundaries, it'll be fine. But for a complete guy, there's no issue. Okay. Okay, so, So that is up to sign the proof of 1 implies 3. Yeah? You're saying these should be minuses. That makes the most sense because I was pretty sure the rest of these computations were right. So she's saying, in fact, that should be a minus and that should be a minus the way this is written. That would make the most sense. Then that would switch all these last signs, right? Minus, 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 and that would reverse this sign here. Okay, let's skip the hug. I'll just go for a high five. Okay. Proof that 3 implies 1. Okay. Now, this is interesting, even by itself, to go this direction. But now, how can we go the other direction? There's going to be at least one step here that I'm just going to sketch for you. It's sort of a write down in coordinates and compute type thing, but I'll be very explicit about what you need to compute. So how could you possibly use 3 to prove that the Ricci curvature is non-negative? So again, this is just non-negative. So that is, we want to know that if for every function, this implies so if this is true for every x, every t, and every nice function u, then we want this to imply that the Ricci is non-negative. So in particular, that means that we want to pick some point x in our manifold and v inside the tangent space of the manifold. And show that the Ricci applied to the VV direction at this point is bigger than or equal to 0. How do you do that? Well, I mean, in fact, there's only one really reasonable thing to try to do here. I mean, you've got something that for a fixed x now, I mean, x we kind of want to be fixed. I mean, one can guess that the x we want to use up here is going to be this x. And we're going to fix u maybe, so that what we have to play with here is t. So what we're going to want to do is pick a good test function u. to try to pull this information out. So that is what we want. Good test function. Yes, of course the minus sign is wrong, right? Because we got rid of the ddt there, then we have to, great, yeah, okay. Babbling to myself, sorry. So in particular, what do we want this test function to satisfy? I mean, just some smooth test function with compact support, whatever. So there's no issues of anything going on here. So we want u such that the following holds. So smooth function, compact support. Its value at x should be 0. This isn't really anything. I just want this for friendliness' sake. Well, we're supposed to be pulling out that tangent direction here. So the reasonable thing to do here is to say that the gradient of this function at x is our desired v. And now here's sort of the key moral that you want. You want this function here. I mean, it doesn't care what it looks like globally, but in the neighborhood of x, you want this thing to be as close to a linear function as possible. I mean, y we'll see when we compute. But morally, we want this thing to be as linear as possible. And there are limitations on a Riemannian manifold of how close you can get. But what you can do is you can insist that the Hessian of u at x be 0. This is possible. I'll tell you roughly how you build such a function. And I'm going to throw in a fourth condition here, which, by the way, is completely unnecessary in the computation, but it lets me throw away a term instead of saying, OK, well, this term appears on the left-hand side and appears on the right-hand side, and if you combine it right, they all cancel. I don't want to deal with that, so I'm just going to assume the fourth term. But it's not so important, so I just sort of put a star there. And that's that the gradient of the Laplacian of u. So the Laplacian of u at x in particular vanishes, right? I'm going to say the gradient of the Laplacian of u at x is 0. This is really not important, but it'll make life happier when we compute. So how to construct? Roughly. In fact, it's very, very easy. Right? So we're going to build it in a certain coordinate system. Namely, we've in fact only really introduced one good coordinate system at this point, exponential coordinates. So at x, right, we had this mapping from the tangent space at x into M. And it had the property that, at least in a neighborhood of x, it was a diffeomorphism. So it was an honest coordinate system in a neighborhood of x. And we're going to let in coordinates u be an actual linear function. So that is, we just pick some coordinate charts. We have our exponential coordinates to some neighborhood of the tangent space in u. And with respect to our coordinates, x1 through xn, we just let u be an honest linear function whose gradient at that point is this. And now the point is you have to check that in these coordinates this is satisfied. So the point is that certainly in coordinates the second double derivatives vanish because it's linear in those coordinates. But the key property about the exponential map is that when you compute the gradient in these coordinates, the Christoffel symbol vanishes at the origin. So that means that the Hessian and the second double derivatives are actually the same at the initial point 0, x. So that if this is satisfied in coordinates, it's actually satisfied invariantly in the Hessian sense. So that's it. That's how you pick this function. And you can check it satisfies this too if you want. But again, that's not necessary. OK. So with that sketched out, how do we use such a u? So obviously what we want to do here is just plug u into this formula and see what happens. But more specifically, what we really have to do here is take an asymptotic expansion. So that is, we want to apply this Bach-Ramaire gradient estimate up here to this function u, evaluate at x, and ask, as t varies, I mean, this is some smooth function of t, and we want to know what's its Taylor expansion around t equals 0. And in fact, we just have to know the first couple of terms of the Taylor expansion. We don't have to go that deep into it. So note first that with our u fixed, that at t equals 0, well, the value of this thing, so the left-hand side or the right-hand side, and the value of this thing, just for the sake of argument, say the norm of v is 1. So it's a unit vector. This is completely irrelevant. Well, I mean, the t is 0 in both cases, so this is just the gradient of u at x. And that's v, which is 1. Right? So if we're doing a Taylor expansion of this thing on both sides in terms of t now, I mean, the leading order term is just 1. Now, what we really want to check is the second leading order term. So that is, if we want to write this as being, a constant plus something times t squared, how do we evaluate what that constant times t is? Well, you take the derivative of the thing at 0. That's it. It's Taylor expansion, right? So we're also going to compute now ddt of, you can do both sides, but the computations are different, so let's do them individually. H sub t, the gradient of u squared at x at t equals 0. Well, what is this thing? This is just equal to the Laplacian of h sub t of the gradient of u squared, evaluated at x at t equals 0. So this is just equal to the Laplacian of the gradient of u squared at x. So what that's saying is that this term here, wait, I really feel I want a different blackboard for this. What can I erase? Whatever, we'll come back to it. The same computation over here. Well, now we have to use Bachner's formula for this thing, right? So Bachner's formula tells us that this is equal to the Laplacian of the gradient of h to u squared plus, is this a minus sign now? Make sure I don't miss this. Now it's a minus sign. Minus 2 times the Ricci of the gradient of h sub tu, gradient of h sub tu, minus 2 times the Hessian of h sub tu squared at x. But at time is equals 0, what is this thing? Well, that's nothing but the Laplacian of the gradient of u squared at x minus 2 times the Ricci of VV minus, well, it's the Hessian of u squared at 0, but this is 0. Right? So it's just this. Good. But what does this mean now? So let's be very explicit about this because I have enough time to finish this, but not enough to actually start a next section, so we can be very careful and slow about this. This is telling us that h sub t of the gradient of u squared at x, well, it's equal to 1 plus the gradient, the Laplacian of the gradient of u squared at x times t plus O of t squared. And on the other hand, we have the gradient of h sub t u squared of x. Well, it's equal to 1 plus, well, what's the t term? It's plus the Laplacian of the gradient of u squared of x minus 2 times the Ricci of vv times t plus O of t squared. Yeah, in fact, I'm pretty sure when I did my notes, I did my computation wrong because I don't need this at all, and that just disappears. So what, though? So what's our assumption? Our assumption, right, is that this term here, I mean, this is some u, some t, some x. This is less than or equal to this for all t. That's our assumption. So we have this is less than or equal to that. Well, what does that imply? This implies that 1 plus the Laplacian of the gradient of u squared at x minus 2 Ricci vv times t plus O of t squared is, I'll uncover that in just 1 second, less than or equal to 1 plus the Laplacian of the gradient of u squared at x t plus O of t squared. But just cancel stuff now and see what happens. So what cancels? The 1's cancel. The Laplacian of the gradient of u of x squared's term cancel. And if we shove the Ricci on the other side, what we end up getting then is that O of t squared is less than or equal to 2 times the Ricci vv times t. Well, that's just done. Or the Ricci of vv is bigger than or equal to O of t. Just let t go to 0, right? So this implies the Ricci is bigger than or equal to 0, as claimed. So the point is we picked out a test function here that exactly pulled out this Ricci term inside these computations. So we could reverse and get the opposite direction. Yeah, that minus sign would have bit me here, too. Okay, good. So, having once again gotten halfway through my lecture, tomorrow, where we'll pick up is to study, well, actually one of two things. I haven't fully decided. Over the next 2 days, we're going to study the following 2 things. We're going to introduce Gromov-Hausdorff convergence. So that is, I mean, when you're doing analysis on Rn, I mean, a key point here, right, is you have notions of function spaces. And what you use notions of function spaces for are notions of convergence of functions and bounds. It's not surprising when we're studying metric spaces that at some point we're going to need to know how to take convergence of metric spaces. Right? So the Gromov-Hausdorff is sort of the first foray into it. There's actually lots of ways at this stage of doing it, but they all kind of have the same feel to them. So we'll introduce the Gromov-Hausdorff topology and how to actually get convergence of metric spaces. And more importantly, to show that spaces with lower Ricci curvature bounds are pre-compact in this space. So that this is the really important part. It means if I get any sequence of Riemannian manifolds with a lower Ricci bound, I can, after passing to a subsequence, actually converge to a metric space out of it. And then most of the theory that we want to build is about understanding what that metric space looks like. I mean, well, what you should compare this to is that you could have had like a sequence of functions in Rn, which were all bounded by say, the first 10 derivatives were all bounded. And you were told they converged in L2 to some function. Right? So you've got this weak notion of convergence to what a priori is just a weak function, right? I mean, like here we've got this collection of manifolds which just converge weakly to some weak metric space, right? But the fact that they had a C10 bound means that with no other work, you know this thing lies in at least C9 plus alpha for all alpha or some nonsense. And 10th derivatives in Lipschitz at least, right? So you do, even if the convergence is weak, you know more about that limit space, right? So in sort of this scenario, you don't know how to get strong notions of convergence, so we pass convergence in a weak sense, but we still build structure on the limits. And that's what we'll talk about. And we'll also talk about in the next couple of days the splitting theorem, which is somehow the first really good rigidity theorem for this, which lets us actually build the structure theory. But I'm done 2 minutes early.